is we are researchers in power electronics. Our role is to develop the power electronics of the PPU. One of the main goals of this European project is to increase the power density, so to increase the to decrease the weight and the volume of the PPU unit. Next slide, please. So actually, we are focused on the radio frequency generator. So before has been the whole thruster has been presented, and we are focused on the generator that is supplying the radio frequency coil. Okay, that is part of the thruster, and there is at least as it is shown here, this coil needs to be supplied with a high frequency sinusoidal current. Okay, a high frequency at about 700 kilohertz, 800 kilohertz, even 1 megahertz, depends on the, but they are high frequencies. Okay, and we need to deliver quite a lot of power. In this case, we are developing a prototype that is for 1 kilowatt, but as has been previously presented by Ariane, there are other power demands for higher propulsion. Okay, so here you can see the architecture of the radio frequency generator. So we have a first stage that is a DC isolated DC to DC converter. So basically, this DC to DC converter is providing isolation that is required for the application, galvanic isolation, and then from the input voltage that is regulated is DC input voltage 100 volts. We need to regulate at the output to provide at the output a voltage between 15 and 200 volts. Okay, DC voltage again, just to control the power that we are injecting to the thruster. And then we have, after the second stage is an inverter, a DC to AC, a high frequency inverter, because it needs to generate a high frequency sinusoidal current. Okay, next please. Okay, so before going to the details of to see how we are dealing these two stages in the project, let me give you some overview of the key technologies that are allowing us to let's say to face the challenges of this project. Okay, first, for probably most of you are familiar with the switching converters, but just let me give you a very fast overview for those of you that are not familiar. Here we have in this picture we have a topology for a power converter, where you can see the MOSFETs. They are basically switches that are switching at high frequency. Typically frequency, I mean, if you are using silicon, can be about 100 kilohertz, 200 kilohertz, something like that. And then you have inductors, you have transformers, so you have passive components, magnetics, inductor transformers, and then you have capacitors. Okay, so one of the key problems or the key challenges in this project is to reduce the size of the passive components that normally are one of the more dominant elements in the size of the power converters, the inductor, transformer, and the capacitor. And in order to do that, we need to switch at very high frequency, okay? Because finally, in these passive components, we are storing energy, okay? And that energy is delivered to the load as depending how we modulate the switches, okay? The semiconductors. So if you are able to switch at high frequency, then you are able to, you don't need to store too much energy in the inductor, in the passive components. And then if you are able to reduce the stored energy in these passive components, you are able to reduce the size, basically. I mean, just to give you a flash message, okay, here on why we need to switch at very high frequency. On the top of this picture, top left, you can see how is the voltage and the current on one of these MOSFETs, one of these switches that are switching at high frequency. So the red is the voltage, that is a kind of a square voltage going up and down. And then you have the current through the switch. It finally behaves like an ideal switch that you open and close. So when the MOSFET is, when the switch is on, then the current is going through. And then when you open the switch, the current should go to zero, go down, and the voltage go up. But this is not an ideal transition, and you can see here that there is an overlapping of voltage and current when they are changing, and that is producing losses. We can move to the next slide, please. So you can see here in this slide in blue how is the losses, the power that is lost every time that the switch is being open and closed. So there is a peak of power that we are losing, and the higher, well, there is a peak of energy. Okay, just to be accurate, there is a peak of energy that we are losing every time that we switch up, on and off, and then the higher the frequency, the higher the losses that you have, the higher the power losses that you are losing. Okay, so of course I mentioned before that we would like to switch at very high frequency, because in order to reduce the passive components, but one of the disadvantages is that we lose more energy. However, there is new technologies that are wide bandgap devices, silicon carbide and gallium nitride, that are a key driver technology in order to allow the converters to switch at higher frequencies. There are several reasons that makes these devices to have better behavior at working at higher frequency. Maybe we can move to the next slide, please. Okay, thank you. Here we have, I mean, just some parameters, physical parameters of this technology. You have the silicon in the first column, then the gallium nitride, and then the silicon carbide. For example, if you take a look to the electron saturation velocity, you can realize that this velocity is around 2.5 times higher in these wide bandgap devices. If you take a look to the critical electrical field, there is a big change that is even 10 times higher. The electrical field that is able to stand the gallium nitride or the silicon carbide compared with the silicon. So these are some technology reasons why these devices, silicon carbide and nitrogallium, are able to switch at much higher frequency without increasing the losses. Okay, we can go to the next slide, please. So here you can see a map of where are the power and the frequency more appropriate for each technology. Okay, so you can see on the bottom, silicon devices are appropriate to switch at a low frequency and power. Okay, on the y-axis you have the power, on the x-axis you have the frequency. So you can see in blue, dark blue, the silicon. You can see that they are able to manage high power, even up to a few kilowatts, but at low frequency. But if you try to switch at high frequencies, the power that silicon is able to manage is going down. However, on red, on the right, you can see that nitrogallium is able to manage similar power levels, but at much higher frequencies. Okay, and much higher frequencies means a lower size for the passive components. Next, please. Another way to see the advantages of the nitrogallium compared with the silicon is this figure of merit. This is just a more electrical figure of merit. That is the RDS-on. The RDS-on is the resistance of the switch when it is conducting. Of course, it's expected to be zero, but it's not zero in reality. You have some conduction losses when the switch is on, times another figure, another that is the charge of the gate. This charge of the gate is the charge that you need to inject to the device to turn on the device. And finally, it's interesting to have a low charge in order to reduce the switching losses. Okay, so this figure of merit, an ideal device should have a figure of merit 0 or very small. Okay, very low charge and very low radiation. In this case, in this figure, you can see in the x axis, you can see the how is the drain to source voltage. So the breakdown voltage of the device. So and on blue you have the silicon technology. The blue line is the silicon technology. You can see that it presents a higher figure of merit than the green lines that belongs to different technologies of GaN. So as I mentioned, the lower the figure of merit, the better the technology. So when the breakdown voltage of the device is low, silicon and GaN are, okay, GaN is better than silicon, but the differences are not so big. However, when you move to higher voltages, you can see that the figure of merit, the difference is even 9 times higher, the figure of merit of the silicon compared with GaN. Okay, so this is another way to show you why GaN is better than silicon. Okay, when you switch at high frequencies. Next, please. Well, another enabled technology that we are using in this project is the digital control instead of using analog control. Digital control has some advantages because it is you are able to control, let's say, more advanced solutions. In order to optimize the design of the radio frequency generator, you can move, for example, you can see here LLC converter with a matrix transformer. You can see that there's plenty of switches. So if this solution is more optimized, but of course the control of this solution is more complex. And in some of these applications, if you use digital control instead of using analog control, then you are able to manage better or to do a better or more appropriate control of the topology of the converter in order to optimize the performance. Okay, so digital control, again, from this point of view, is also let's say, enabled technology that allows us to go for higher frequencies, and finally reducing or increasing the power density of the converters. Next, please. Okay, no, please. Sorry, can go back one more? Thank you, Linda. Yes, on the right. Great. On the right, you can see here the waveforms, the voltage of a MOSFET and the current of a MOSFET for a resonant converter. I like to show you this because we are using some of the solutions that we are considering are resonant converters. You can see in the previous figures that I showed you, the current was a square waveform like the voltage. And as you remember, when the voltage was going down, the current was going up, and then there was some overlapping. However, you can see in blue is the voltage, and in the pink waveform is the current. When the voltage is changing from one value from the high value to the low value, the current at that time is 0 or close to 0. That happens in resonant converters, and that is an advantage because then the switching losses are or 0 or much lower than in PWM converters. Okay, so that is why we are also considering this type of topologies, these resonant converters. So please, next. Okay, here I would like to show you the back converter is a multi-phase back converter, another topology that we are also considering in this project. You can see that on the left, well, we are applying let's say a an advanced control where the currents are triangular, but they need to be negative, and when the MOSFET is being turned on or turned off, in order to achieve what is called zero voltage switching, that is making the voltage zero when the MOSFET is going to switch. And again, the goal of this is to reduce the switching losses in order to be able to work at very high frequency. So, for example, this control, which is quite advanced, quite complex, the control algorithm for this control is complex, and if you do it with digital control, you are able to make a more appropriate control, a more optimized control of this topology. Okay, so again, digital control can be an interesting approach technology to optimize these converters. Next, please. Finally, we cannot forget the magnetic components. The magnetic components, let's say, are the component that is suffering the increment of the frequency. We mentioned before that the goal is to increase the switching frequency to reduce the size of the capacitors and the magnetic components. However, increasing the switching frequency is when you increase the switching frequency, the magnetic component is suffering because the losses are being increased. The core losses of the magnetic component are increased, and also the conduction losses, because there are high frequency effects in the magnetics that are being to be more critical when you move to frequencies close to 1 megahertz of hundreds of kilohertz. So finally, the design and optimization of these devices is very critical. In this project, the PPU project, we are collaborating with another partner of the consortium is Frasa, that is a Slovenian company. They are experts on the design and optimization of magnetic components, and we are collaborating with them in order to optimize the magnetic components. Next, please. Okay, let's take a look to some details of the designs that we are doing. So let me remind you how was the architecture. We have the DC-DC, isolated DC-DC converter, and then we have the inverter later, the DC to AC in the second stage. Let's focus on the DC to DC converter, the isolated one. Next, please. Okay, this is just to show you the methodology. We are considering the design and optimization of these topologies is being very complex, and we are still working on it. Here you have a picture of one of the solutions that we are considering. What we are doing is to do a design of the solution, of the topology, just running simulations, just to verify that electrical simulations, just to verify that we are able, the design that we are doing is able to work under all the operating conditions that should work. And then also on the right, we create a model, a losses model, just to calculate the losses that we have, in all the different operating conditions. Okay, you can see, for example, the blue line on the right, where the losses are changing depending on the output voltage that we have. You can see that there is a step. In the blue line is going. If we move from right to left, when we move to lower voltages, the losses are going down, but suddenly the losses are increasing. The reason for that is because we are losing zero voltage switching. Okay, so if on the right side we are able to have zero voltage switching, and then we are reducing a lot the high frequency losses. However, when we lose zero voltage switching, then the losses are going up. Okay, but this is just an example of, so we are analyzing very different topologies, doing the design, doing simulations to be sure that we are able to work on all the operating points, and we calculate the losses at the different operating points, and then we are comparing losses and size of the magnetics and size of the capacitor, just to have a whole overview of the solution. Next, please. Thank you. Okay, this is one example of the magnetic components design that FRESA has done. Okay, FRESA is doing the design of the magnetic components, and then they provide us the information, and then we consider that in our design. Okay, we incorporate this feedback in our design. Next, please. Okay, and here, this is just an example where we are creating a bigger table like this one, considering different topologies. And then we consider how many GaN devices we need, which are the losses that we have, which is the losses and the size of the magnetic components, which are which is the size of the capacitors, and then we account for the total volume and total losses of these devices, just to compare. We are still, this table is still alive. We are considering other solutions. Okay, next, please. Now, let's focus on the second stage, the inverter, the AC to DC converter. The topology for this inverter is quite simple. Basically, is what you see here. Is two switches that the S1 and S2 that are creating the blue square voltage that we have on the right. And this square voltage that must be at high frequency, at the frequency of the thruster. Let's think about 700 kilohertz, close to 1 megahertz. Then we have a resonant capacitor that should resonate with the load, okay? And the load, which is quite complex, but basically can model by this behavior. I mean, the RF, the radio frequency coil is the load for this, for our RF generator. The load is can be modeled by an inductor and a resistance, okay? And the resonant capacitor must resonate with the inductor. And then if we are able to switch at the resonance of the capacitor, at the resonance frequency of the capacitor and the inductor, then you can achieve the nice waveform that you have on bottom, the red waveform, that is a sinusoidal current that is circulating through the radio frequency coil, okay? That is the optimum waveform to have a let's say, appropriate operation of the thruster. And then, depending on the voltage that we apply at the input of this inverter, radio frequency inverter, then we modulate the current to be higher or lower, and finally we're controlling the thrust.